Welcome back again for this lecture on impacts of climate change on water resources. I would like to again acknowledge my past PhD students and the project staff, Dr. Subhimal Ghosh, Deepashri Raje, Shaikh Rehna, Arpita Mandal, Ujjwal Saha, Chandrarupa and Ila Chawla. These are my PhD students, and Harshita Gupta helped me putting together this lecture. So, in this lecture what we will do is we will start with the current water stresses in India and then look at the climate change impacts on various hydrologic variables, for example, stream flows, evapotranspiration, urban floods, riverine floods and so on. And also to some extent we will look at uncertainty quantification in the impacts. In doing so, I will emphasize more on the Indian case studies, although I will also talk a little bit about the Colorado River based system. So, as all of you are aware, we are already a stressed country as far as water is concerned. The first level of stress comes from a decreasing per capita availability of water. As the population grows and as our demands are increasing, the per capita availability of water is coming down because we have a limited resource. Then what is more concerning is that we use bulk of our water for agriculture, as indeed it is the case with many countries, but our efficiencies of water use are very small. So, low efficiencies of water use. Then groundwater depletion has caused major concern in several regions of the country. Now, what is also important to realize as far as water is concerned is that we are in the state of rapid urbanization. You look at areas such as this, where there is hardly any scope to expand the infrastructure now. Also, many urban areas are stressed because of limited water availability. In fact, in cities like Bangalore and all, we get water from as far away as about 80 to 100 kilometers with a huge energy energy related to pumping and so on. It is also important to see that the manpower available to understand these various issues in the country is extremely limited, and therefore, courses such as these should help in developing that kind of capacity in the country. These are existing stresses. There are also frequent floods, frequent droughts. Kerala floods have just happened, the Marathwada droughts, then Kedarnath floods, etc. So, these extremes are increasing in the country. These are existing stresses, and the climate change is most likely to aggravate the situation. In fact, some of these may have occurred because of the general warming that we are seeing. So, when we come to the water sector, we need to address the following issues vis-a-vis climate change, namely that how do water fluxes vary on catchment scale or river basin scale. As you know, most of our water resources come from our river basins. For example, you have Ganga here, Brahmaputra, these are international rivers, in the sense that Ganga flows into Bangladesh, Brahmaputra comes from China and then goes into Bangladesh and so on. Then you have Mahanadi, you also have Narmada here, west flowing rivers, then you have Krishna, Pennar, Kaveri, Godavari is here and so on. So, these are our major sources of water. So, the first level question that we need to ask when we are looking at climate change impacts is the one related with water fluxes in these river basins, whether the flows are likely to go down, are they likely to go up, whether the demands in those basins are likely to go down, etc. Then on the demands, as I mentioned in the first class, the evapotranspiration has a great potential to be affected by climate change, and the irrigation demands are primarily dictated by evapotranspiration. So, we need to look at that. Then municipal and industrial demands because of rising temperatures and other climate change related issues. Then we also need to look at ecological and environmental demands, whether they are going to increase because of climate change and so on. What is less addressed is the impacts on water quality itself. For example, lake water qualities, the river water qualities which are receiving non-point source pollution, whether they are likely to be affected, and in fact, there is evidence and there is some work which shows that in fact, the water quality will be affected with rising temperatures and so forth. What is also important for our country is the frequency and magnitude of extreme events, floods and droughts, and to pinpointedly attribute a particular event to climate change as of now seems to be difficult, but needs to be done. But what is possible, however, is that the change in the frequencies or the expected change in the frequencies because of climate change, frequencies of floods and droughts because of climate change is possible to be addressed. Then of course, for our country, delays in onset of monsoon is extremely important because it has a huge implication for agriculture. Then as I mentioned in the first lecture, salinity intrusion and coastal flooding. So, these are the major issues that we need to look at, and this is the same figure that I put up in the first lecture. The way we go about assessing the impacts are that we first pick up the climate change projections from the GCMs, the global climate models. We downscale them to the hydrologic scales. These may be available at let us say 100 kilometer scale or about 1.5 degrees scale, and we bring it down to station scale, or if we are looking at gridded data, we may be bringing it down to 10 kilometers, 20 kilometers and so on. Then the topography, land use, land cover, all of these catchment processes, we project them also into future, some of them at least, land use, land cover, and then we run a hydrologic model to get the possible future water resources scenarios at river basin scales, and then start looking at adaptive responses arising out of these kind of projections. So, this is by and large the process that we adopt. One of the most significantly studied river basin is the Colorado River Basin in US, and this has 12 major river reservoirs. For example, the Hoover, the famous Hoover Dam is here, number 7, and then that is here. You also have 7 states. So, much like it happens in India, there are also interstate conflicts for water sharing or interstate issues, if I want to avoid the word conflict, interstate issues associated with water sharing, and there is a famous Colorado Compact that governs the water sharing. Now, in this particular study, the reference is here. What they do is they use one climate model, the parallel climate model, and one hydrologic model, the variable infiltration capacity model, and then simulate to the future the stream flows and the evaporation. For example, the precipitation, all of these variables, precipitation, evaporation, runoff and so on. So, this is the historical period, that is 1950 to 1999, and control is 1995. By control, we mean we hold the particular CO2 level at this level, 1995 level. So, that is called as a controlled climate simulation. Then we may have BAUs, that is business as usual scenarios, which means that you allow the CO2 to keep increasing and then simulate what happens to precipitation, what happens to evaporation and so on. Now, what is important for us to see is this particular figure, which means the precipitation seems to be more or less same, not too much of a change. However, there may be changes in the runoff. Now, the change in the runoff may be very small, about 2%, 3%, etc. Maybe it may go up to 10% for this particular model scenario combination. But what happens is that if the demands in the basin are almost equal to the mean flow, and then the mean flow starts coming down, that will affect the water availability. For example, they conclude that the Colorado River Compact, as I said, it governs the sharing of water among these 7 states. So, in the 80% of the years in the control climate simulation, which means if our CO2 levels were at 1995 level, then about 80% of the years of simulation you would have met the Colorado Compact. Whereas, only about 59 to 75% of the years, which means that the water sharing gets affected, as well as annual hydropower output significantly reduced for all simulation, all the future simulations and so on. So, these are the sort of inferences that you can draw. I would alert again that this was a preliminary type of study which was used, which used only one climate model and one hydrologic model, and then provided the projections. Similar to that, for as a response to the NATCOM project, this study was done by IIT Delhi. They used a had regional model. This is at 0.44 degree scale, and for one particular scenario, and they then simulated all of these, for example, all the hydrologic components, for example, the stream flow, the evapotranspiration and so on. Because this model that the SWAT model is a hydrologic model, this uses these inputs, solar radiation, wind speed, relative humidity, etc., and simulates runoff and evaporation. This study was done for several large number of river basins, and the individual river basins were divided into smaller river basins, smaller basins, sub basins of the size about 5,000 to 10,000 square kilometers. So, when we do this, we get situations like this. Remember, you must understand this with the caveat that only one model and one scenario was used, and this was a large level first level response to be provided to NATCOM at that time, and therefore, the rigor that is now possible was not actually applied at that point, but however, this gives a good indication of how different river systems are likely to behave under certain situations. For example, you look at the control scenario. Control is that you are controlling the CO2 level. GHG is you are allowing the greenhouse gases to increase according to that particular scenario, IS92A scenario, and this is for a particular regional model. So, in the GHG scenario, the rainfall is likely to increase in Mahanadi basin, Brahmani. So, this gives, as long as this is positive, it indicates that there is an increase in the rainfall, 18.6%, 18% and so on. Once we come down to Narmada here, that is in the peninsular region, no, in fact, not necessarily peninsular, because Godavari, Kaveri, they are also likely to increase. But Narmada goes down minus 2.4%, Tapi and so on, like this. But the already stressed systems such as Sabarmati, Luni, Mahi, etc., these are likely to, as far as that particular projection is concerned, these are likely to show a significant decrease in the rainfall. Similarly, we look at the runoff, then as a proportion of rainfall, what is happening to runoff, then actual evapotranspiration, then as a proportion to rainfall, what is happening to evapotranspiration, evaporation and so on. Now, these kind of inferences you can draw using a hydrologic model, coupling it with a climate model, not necessarily online coupling, but picking up the projections provided by the climate models and using them in the hydrologic model. Now, let us go slightly deeper into it and then look at how exactly we do this. We take, for example, the Tungabhadra river system in Karnataka. It is this area that we are considering up to Tungabhadra dam, and this is the study area. We pick up the soil types, because in hydrologic models the soil types are important and soil data is necessary, and typically we get the soil data from global data sets or our NBSS LUP, National Bureau of Soil Surveys and Land Use Planning. Now, these organization, government organization gives the soil data. So, from the soil data we get all the hydraulic properties of the soils. Then we need the land use, land cover for that basin. For example, how much is the agricultural area, how much is the vegetated area, and so on. And there are some scrub forests, dense forests, and so on. In this particular case, urban area is there, mixed forest, forest evergreen, etc. Now, these land use, land cover patterns are also available through global data sets. Now, in fact, our own Bhuvan, which is ISRO organization, ISRO created website. This gives extensive high quality data on most of these river basins. So, what we then do is, first we set up the hydrologic model for that particular river basin. When I say set up, we use the historical data. Let us say that this is your basin and you have stream flow at several locations, observed stream flow at several locations of that. We use the observed stream flow to calibrate the model. That means, we have the model parameters, we calibrate these parameters such that we are able to simulate the observed stream flow to the best extent possible. That is called as a calibration. And then we also do the validation by removing part of the data that the model has not seen, and then we allow the model to run during that period and validate the results. So, these are details of calibration and validation. Once you have a calibrated and validated model, then you change the input according to the climate projections. For example, the input may be precipitation, and for this particular location the precipitation would have been projected in certain manner. Actually, for precipitation and other hydrologic variables, we do the downscaling from larger scales, we bring it down to smaller scales and then run the hydrologic model. Once you run the hydrologic model, you will get all these variables, such as for example, the observed flows at those locations, the base flow, which is the groundwater contribution, and so on. Now, there is another small detail that you must inform your students, that some of these variables that I talked about, the climate variables, for example, I was talking about relative humidity, we also talked about wind speed, etc., which are used as predictors for precipitation. Now, historical data on these variables may not be available, in which case we fall recourse to what are called as the reanalysis data, and you can get these reanalysis from several products, globally available products. Typically, we use the NCEP NCAR reanalysis products. So, this is some detail that you may want to emphasize on when you give some projects or some such thing to the students. So, with this then we will be able to project into the future how, with respect to the baseline, for different scenarios, how the flows are likely to change. This is only baseline here. So, with respect to the baseline, how in 2020s, 2050s, etc., how the flow is likely to change. As you can see here, the baseline is somewhere here, and most of these models for these scenario, this model for this particular scenario shows that there is likely to be an increase for A2 scenario. Similarly, for B2 scenario, this is the baseline and it is likely to increase, and this is a average monthly flows that we are talking about, and the monthly flows are in Qmax, cubic meters per second at that particular location. So, when you plot the time series into the future, let us say from 2011 to 2095, 99, etc., you must also remember that as you go farther into the future, the uncertainties will increase. So, typically, although we simulate into the far future, we use up to about 40s or 50s for impact assessment and adaptive responses. So, this shows a general small increasing trend for the Tungabhadra basin. As far as flows are concerned for A2 scenario. Similarly, for B2 also there is a slight increase that is there. But what is important to realize is it is not just the stream flow that you get. You calibrated the model with respect to the stream flow, but you also get with respect to the historical period all the water component. For example, excess runoff, precipitation, how it has changed, the actual evapotranspiration, how it has changed, how the percolation has changed. Percolation also governs the recharge to some extent. So, this is the baseline observed period, and this is for A2 scenario. This is 2050 A2, 2080, A2, etc. So, all of these details you will be able to get. This is again for one model and two scenarios. But the point that you must emphasize always is when we are talking about future projections, the number of models you must include as many number of models as possible and as many scenarios as possible, and then start looking at the ensemble of projections. Now, we will also talk about the Mahanadi stream flow at Hirakud reservoir. One way of doing this is project the rainfall first, run the hydrologic model and then get the stream flow. But this will introduce an additional component of uncertainty because the hydrologic model has its own several parameters. So, instead of developing a statistical relationship between the GCM simulations and the precipitation, we bypass the precipitation and directly come to stream flow. And for stream flow, we use the predictors which govern not only the rainfall, but also the evapotranspiration, because evapotranspiration becomes an important variable when we are looking at stream flow. And we look at monsoon stream flow at Mahanadi river, and this is the location of the Mahanadi river. So, these are the predictors that we use, and then we produce what are called as the flow duration curve. I will explain presently, but this we do for several models and several scenarios. For example, Miroxi 3.2, then A1B, A2, B1, CGCM2, etc., all of these. So, several model scenario combinations we do, and then produce with respect to the historical flow duration curve, how the flows are likely to change. What does the flow duration curve give? It gives for a particular level, let us say 60% level, what is the flow that is equaled or exceeded. These are the percentages that generally are used in the planning. For example, what is the 75% reliable flow? It means that 75% of the time this particular flow is equaled or exceeded, and that is what they use in the planning purposes. If many of these flows, especially the middle flows projections, show that there is likely to be decrease, in fact, we can integrate these and then provide one ensemble average. If the ensemble average shows that the flows are likely to decrease at that particular location, that will have a serious implication on water use for irrigation, hydropower and so on. So, for the same Mahanadi river and at the same Hirakud reservoir, there are other studies that are available, Ashokan and Datta, who showed how the irrigation demands are likely to increase. Similarly, they have also shown how the projected peak and average discharges are likely to behave. It is instructive to again remember that your seasonal flows may either remain the same or perhaps may decrease or may even increase, but the peak flows may still be going high. So, for example, these are the peak flows. So, this is increase in peak flows, this is a percent increase. So, which means whatever peak flows, flood flows we are seeing, perhaps in 2025 it may increase by 15 to 20% and so on. So, we need to address all of these. On one side the stream flow may be going down, the demands may be going up and the peak flows are likely to go up. Then we develop what are called as the adaptive responses. We look at the Hirakud dam and then see how this flood storage needs to be operated while maintaining whatever is required for hydropower and whatever is required for irrigation. This we do through optimization and then provide what are called as the adaptive policies, especially during the flood period, 1st July to 2nd October, how this reservoir needs to be operated. Now, this has several details. Right now, please do not worry about all those, but you just emphasize on the fact that you need to relook at how the reservoirs need to be operated given the projections on stream flow as well as on the flood peaks and so on. I have been talking about the irrigation water demands, and it is important to know that our country uses almost about 75 to 80% of the water available for irrigation, and the efficiencies are small. In such a scenario, what happens if the evapotranspiration starts increasing because of the climate change, and these are the climate variables that will affect the evapotranspiration, as I said in the first lecture. So, what we do is we examine for a particular small catchment. This is a Bhadra command area in Karnataka. we take this particular small catchment and then see what type of crops are grown for which the water is being supplied by this particular stream at the reservoir, and how the evapotranspiration demands of those crops are likely to change. So, we use Mirox 3.2 with A1B scenario in this particular case, and then these are the predictors. As I said in the morning, if you are in a doubt, you put the predictor into the basket rather than eliminate it. You take large number of predictors which you suspect are affecting the particular variable. In this particular case, let us say I am talking about precipitation, I may be talking about relative humidity, I may be talking about maximum temperature, which all affect the evapotranspiration. In which case, you take all these variables and then do some kind of a correlation analysis and others more sophisticated analysis for that particular variable to filter out the predictors. Now, we using these, we downscale rainfall, maximum minimum temperature, wind speed, relative humidity, etc., because these will all affect the crop water requirement. Now, these are the results. I will just explain one part and then leave the other. See, for example, rainfall. I would have used some of these predictors for rainfall and then used a particular method of transfer function approach. In this case, what we use is what is called as a canonical correlation analysis, which does simultaneous downscaling at several locations. Anyway, that detail you please do not worry. So, at location 1 we get this kind of projection, that is Meroc 3.2 simulated, that is green. On this scale it is very difficult to see, but you look at these uncertainty bands, which means that there is a variation in the rainfall with these kind of uncertainty bands. Similarly, at all these locations we get for rainfall. Similarly, we get for relative humidity and wind speed, and we get for maximum temperature and minimum temperature. The procedure remains the same, that you use for maximum and minimum temperatures, you use certain predictors, use a transfer function approach, bring from larger scales to smaller scales. That is the idea, and then you plot these what are called as the box plots, which are essentially which show, for example, this may show a minimum value, this may show a median, and this shows the maximum value, and so on. Now, these details are this can be either median or mean, etc. So, these you can use from the data, you can generate from the data. These are called as a whisker plots or box plots. So, you get this kind of picture for all the variables. Then, so on one hand you have downscaled the precipitation and temperature and the relative humidity, etc. This we converted to evapotranspiration. This is called as a reference evapotranspiration. For example, you may use the Penman-Montes type of equation, which uses T max, that is a maximum temperature, minimum temperature, relative humidity, vapor pressure, etc., and then generate with respect to the observed how the evapotranspiration is likely to change. For example, you look at certain periods like April, May, these are the summer months, June, July, etc. The evapotranspiration, reference evapotranspiration is likely to be much more significantly higher compared to what is there for the observed period. This information we convert into the actual water requirements for various crops. For example, paddy, how it is likely to change, sugarcane, semi-dry crop, etc. There are ways, simple ways of accounting for the crop factors, season of the crops, and so on, and then convert that into annual water requirements. So, you will see that the flows are likely to go down, but for the given cropping pattern, the requirements are likely to go up. So, we need to develop adaptive responses. The urban floods are very commonly occurring in our country, as indeed across the world. Urban floods, remember, are driven by short duration high intensity rainfall, unlike the riverine floods. So, we need to address how the short duration high intensity rainfall is likely to change. What happens to hydrology in the urban areas? For example, as I said, this is a urban area and this is a pristine watershed. The same intensity happens in both of these. The response of this will be much more smoother, much more sluggish in the sense that it will generate runoff at a much slower pace. So, after urbanization, whatever rain that falls here has to convert itself into runoff immediately, and therefore, if you plot the discharge versus time, the discharge quickly peaks here in the urban area, whereas in the non-urban area it will be a smoother function like this. The peak is higher, the time to peak is much smaller, and the total runoff generated is much higher. All these three characterize the urban hydrology. So, we look at Bangalore city and we see that in the recent past the temperatures have increased significantly. This is just the past. Similarly, we look at the past rainfall. As I said, the duration of the rainfall which causes floods is much smaller in urban areas, for example, 1 hour, half an hour, etc. The IDF relationships provide, these are called as the intensity duration frequency relationship. For a given duration, for a given frequency which is a return period of 10 years, what is the intensity of rainfall millimeters per hour, that is what is provided by the IDF relationship. So, we look at the distant past 1969 to 1986 and then we look at the nearer past which is 1987 to 2003, and if you take the entire record, what happens. So, in most of these cases we are seeing that there is a significant increase in the past of high intensity rainfall which causes the floods. Then we ask the question, are these likely to increase in the future? So, for that what we do is that we again go for recourse to the climate models. Climate models, much as they work well for large spatial scales, also work well for large time scales, but in urban areas we do not have the luxury of using large time scales. So, like we did for spatial scales, from larger scales to smaller scales, we also do for time scales. From larger time scales we bring it down to smaller time scales with what is called as disaggregation. We do downscaling on space, disaggregation on time, and reconstruct the IDF relationship. This is the intensity duration frequency relationship. We reconstruct that for a given RCP using 85 simulations in this particular case, large number of models with RCP 8.5, and then see that for these durations which actually affect the urban flooding, the rainfall intensity is likely to be much more higher. Whereas, as you progress in time, for example, 24 hours etc., there is not too much of a difference, there is not too much of uncertainty also. So, that brings us to the question of whether we need to re-look at the designs, hydrologic designs in urban areas. Then we look at urban the droughts. You know that our country's large number of regions of our country are drought prone, and drought situations like Maratha droughts etc., have been happening frequently now. So, this is the area we take and superpose the NCEP grid. NCEP is National Center for Environmental Prediction. We superpose that and develop a relationship between precipitation at that location with respect to the surrounding NCEP grids. This is what we do in the statistical downscaling. First, you develop a statistical relationship between these, and then there are a lot of details of how to reduce the number of variables and so on. Right now, do not worry about that. Essentially, if you have precipitation here and if you have several of these locations here, we put this as a function of all of these climate variables. We hold this relationship sacrosanct, and then because we have projections on this available from the climate models, we reproduce the projection, we reproduce the precipitation into the future. In the case of droughts, what we do is we use the drought indicator, standardized precipitation index is a drought indicator. So, we convert the information on the precipitation into standardized precipitation index and then look at how the SPI is likely to change. In this particular case, we use several model scenario combinations, and because there is an uncertainty associated with this, you get in the projection, you get a band of projections. We address the uncertainty through evolution of the distributions, probability distributions. How, for example, in 2007 it behaved, 2020 it behaves, 2040, 2090, etc. Why this is important? This will provide us with an idea of the likelihood of extreme droughts, normal conditions, and severe droughts, etc. So, you have extreme droughts, mild droughts, severe droughts, etc. So, these kind of probabilities will help us in managing the agriculture related activities, because if you know in advance that over a period of time the droughts are likely to increase in certain manner, then you should be able to adapt to such things. Then we have the question of floods and droughts. What is happening to the return levels of the floods and droughts? Now, by return levels I mean the magnitude which recurs once in so many years. For example, when I say a return level of 100 years, it means that that particular magnitude of the flood is likely to happen once in about 100 years. We estimate that with the historical data. Now, the future will no longer be like history, and therefore, the question that we ask is how long into the future will the return levels be valid, which are estimated based on the past. The past will no longer provide a clue to the valuable clue to the future because of climate change, and we use this was the work of my PhD student Dr. Arpita Mandal. Unfortunately, we do not have data in India for this, therefore, we address this for Colombia and Colorado. We ask the question for floods in Colombia, if we estimate the historical return periods, how long into the future it is valid? That is a question. Similarly, for the droughts in Colorado River. So, what we estimate is by around 2036, the 50-year return level will be significantly different from what was used. This is a stationary return level which was used based on the historical time period. Now, what is the physical significance of this? That you would have designed, let us say, a dam for carrying that particular flood discharge, which is estimated based on the historical data, and you would have put a 100-year return level, let us say, and you built the dam. But this 100-year return level no longer remains 100-year return level into the future because of climate change. It may convert itself into a 70-year return period, and that is what is implied here. Similarly, 100-year return period, this is valid up to 2073. Of course, all of these conclusions are burdened with site uncertainties and so on. I encourage you to go through all the literature associated with this. So, in summary then, the methodologies that we discussed in the first lecture are now applied to several river basins, and I showed the example of the NatCom which IIT Delhi has done, where for every river basin you superimpose the climate change and then arrive at the projections on several hydrologic variables. For example, the stream flow which dictates the water availability, evapotranspiration which dictates the water demands, and therefore, on river basin scales you will know how this particular river basin is likely to behave in future. Once you have this idea, then you should be able to develop adaptive responses. So, the summary is that the country is already water stressed because of several reasons, and climate change is likely to be a significant additional stress, and we need to understand the impact of climate change correctly. Now, even the most available, most advanced tools that are available today, most sophisticated GCMs and the downscaling methods and the hydrologic models, even with all these, the projections are still burdened with uncertainties, and we need to address uncertainties, communicate them properly, so that it becomes useful for policymakers. Then we have methodologies now, and for large number of river basins in the country, we have been able to estimate the impacts on stream flow, evapotranspiration, water demands, hydrologic extremes of floods and droughts, etc. So, this should be used for policy development and so on. I would like to just add as a matter of information to most of you that the Ministry of Water Resources, that is through INCCC, that is Indian National Committee on climate change, has assigned work to number of IITs and IISc on different river basins just to estimate the climate change impacts on those particular river basins. When you combine all of this knowledge, you will know how the water sector is likely to behave in the next 2 to 3 decades. So, with that I conclude this lecture. Thank you very much for your attention.